Hi. In this video, I'm going to be talking about problem 12 from the Chapter 7b homework, number 7.70 in the Pearson, in the Missouri book. This was one lots of you asked about, and then I gave a few hints about and talked to a few of you about individually, but this is a really hard problem. And as I said in class, it was not actually quite the one that I intended to give when I'm selecting them. I'm reading the problems and I clicked on the wrong one. But I'm really proud of the work that a bunch of you did on this, and I want to talk through it because I think it is a really interesting problem and it's kind of rewarding. So this video is going to have a bunch of stuff in it. It's going to have some calculations and derivations. It's going to have a Desmos graph with integrals and stuff in it. It'll get kind of complicated. But I want to start off with just understanding the problem and the core physical insight that's going into it and what it is we're trying to do. So the problem is imagining that you've got a scientific instrument that you are dropping out of the sky. It's got a mass m, it's mounted to a balloon, it's falling before a parachute opens, and as it falls, it's got an acceleration whose magnitude is GE to the minus T over tau. Okay, that's interesting. That's not how things ordinarily accelerate that we're used to in our physics problems, because we're used to constant accelerations. In fact, most of what we've done this year has been about constant acceleration. So this is a different thing. So I want to talk for a moment about what would happen if the acceleration was constant. If the acceleration was constant and it was our familiar negative 9.8 meters per second squared, then as that package falls, its potential energy is going to be decreasing. So potential energy will decrease. Its kinetic energy will be increasing because it's speeding up. Kinetic energy up. And the total energy will be constant. Total energy constant. Because as that potential energy decreases, the kinetic energy will be increasing to match. Everything will come out even, and no change in total. In that case, no heat would be generated. Heat is another form of energy other than potential and kinetic. And if it's being generated, that means that some of that potential and kinetic must have been converted into heat. So the question is asking, at what rate is energy being turned into heat if we have this function for the acceleration? So I want to think about that. What would happen if you have an acceleration like this that's not constant? Well, let's look at that function, GE to the minus T over tau. This is what this function looks like when I'm kind of zoomed in. If I zoom out some more, you can see that is an exponential decay. It starts off big and negative and gets closer and closer to zero as time goes on. And I put in the value of tau that the problem gives later on, 5.53, to see what that function looks like. And you can see right when you cross over the axis, the value is 9.8 like we're used to. So the value of G is 9.8 at first as it begins to fall. And then G quickly, very quickly, decreases. After 1 second, G is already down to negative 8.1 meters per second. And by 5 seconds, it's down to, I can't read that, 3.9 meters per second. So it's dropping, the acceleration is decreasing really quickly. And it's close to zero within 10 to 20 seconds. You actually see that in the limit, as the problem later talks about, as time gets closer and closer, goes towards infinity, the acceleration is tending towards zero. So what happens if the acceleration of something is zero? If the acceleration becomes zero eventually, so that goes to zero as t goes to infinity, if the acceleration becomes zero, that means the velocity will stop changing. So the velocity stops changing eventually. Okay, if the velocity stops changing eventually, that means eventually the kinetic energy will stop changing. If the kinetic energy stops changing and the velocity isn't changing anymore, that means it's coasting. It's falling down at a constant velocity, which means the potential energy is still decreasing, but the kinetic energy isn't increasing to match. So potential energy still decreases, the kinetic energy stops changing. That must mean that that change in potential energy that's continuing to happen is all being turned into heat. Does that make sense? That's the core of the problem. So basically, we're going to end up asking if the potential energy stops changing, if the kinetic energy stops changing, and the potential energy continues to fall, how quickly is that potential energy being turned into heat? Okay, well, the rate of energy loss is going to be equal to how quickly the potential energy changes. That is the derivative of the potential energy. Well, the potential energy is mass times gravity times how high it is. So that means the rate of that energy loss is going to be equal to, well, the mass isn't going to change, and the gravity is not going to be changing anymore. So that's going to be how quickly is the height changing? Well, how quickly the height is changing is the velocity. So mass times gravity times the velocity. So the question is ultimately asking, we need to figure out how fast it's moving when it stops changing anymore. That'll tell us how quickly the potential energy is changing. And then that'll tell us how quickly the energy is being lost and turned into heat. So that's the key insight. That's the thing that we're trying to do. And all of the math that I'm going to show you in a few minutes is all about trying to figure out that. How quickly is it going to be moving when it stops changing? That's how quickly the potential energy will be changing, and therefore that's how quickly the heat is being generated. Okay, so let's look at some of these equations. I've set up the acceleration function and with the right tau so that the acceleration drops towards zero pretty quickly. So this is what the velocity would look like. So it starts out at zero, and then as time goes on, the velocity steadily increases in the downward direction. And it's going 27 meters per second after 4 seconds, and 41 meters per second after 8 seconds. And it keeps increasing, but you can tell that it is turning over and slowing down how quickly it increases fairly soon. And in the limit, it seems to be approaching a particular velocity. Looks like it's about 54 meters per second. And I could like zoom out some more and see, yeah, it's really close to 54 meters per second. That's the maximum speed that package is going to go, because as the acceleration decreases, the velocity will stop changing quite as quickly. Actually, as a side note, why would the velocity stop changing? Why would the acceleration decrease over time? So the thing that causes air resistance is, as this package is falling, air molecules are bashing into it from underneath. And as they bash into it, they transfer momentum to it that slows it down. Well, the faster it's going, the faster those things are hitting from its point of view, and therefore the more it experiences air resistance. Well, at some point, there's like an even trade-off between how quickly it's being accelerated downward by gravity and how quickly those air molecules are hitting it from underneath. When those two balance each other out, the acceleration will stop. It'll just stay at that speed and coast downwards. That speed can still be quite fast. It depends on the shape of the object and some other things. But the velocity will end up constant after a while. Okay, so that actually kind of gives us most of what we need. The rest of it is going to be like doing some calculus and doing some algebra to be able to figure out the equations that describe this. But we have the right basic idea. Here I've set up an equation that shows the height of the object, and I have it starting from 4,000 meters up so that there's enough time in the air to see what happens. So it's going to be way up there. And you can see that right at the beginning, you have a nice parabola like we're used to seeing, but then it gets straight very quickly. And the reason it's straight very quickly is because the velocity has stopped changing. So eventually, if you drop from 4,000 meters, it's going to hit the ground, and it's going to take, looks like something like 80 seconds to hit the ground from 4,000 meters. So that number is something that I've put into it in order to visualize the problem doesn't give us a height of 4,000 meters. Okay, then I've also got equations for the potential energy, which is decreasing as it falls, and the kinetic energy, which is increasing as it falls. The kinetic energy is the one that we're really curious about here. So let me show that one where we can see it. And you can see that kinetic energy increases and then stops changing after a while because it's moving at a constant speed. And then I've also got the potential energy, the derivative of the potential energy, which was the key one that we really wanted to know. Eventually that stops changing. There it goes. So this is how the derivative of the potential energy is decreasing, so it's negative, but then it stops changing after a while. The rate of it stops changing. It's constant after a while. And then the kinetic energy, flip that around, it increases, the rate of change of the kinetic energy increases and then decreases because it's changing at a constant rate after that. Or actually it's not changing once it gets to 0 right there. Okay, that's the stuff that we've got to calculate here. So let's do a little bit of math using that equation. So if the acceleration is ge to the minus t over tau, then that means that the velocity function is the integral of that. So the integral from 0 to t of ge to the minus t over tau dt. I think that if this were our math class, I might be a little bit more careful about using dummy variables for the integration. But that integral is minus g tau e to the minus t over tau between the integral, between the limits of 0 and t. Because the integral kicks out that 1 over that tau factor. That works out to be minus g tau e to the minus t over tau minus 1, because e to the 0 is 1. Okay, so you can already see how there's a limiting behavior in this velocity function. If the time goes to infinity, then this factor here is going to become 0 because you have e to the minus huge number. Subtract 1, so that becomes g tau. There's a constant value for the velocity in the limit. So the limit as t goes to infinity of v is plus g tau. That's a magnitude. Okay. Then we're actually basically almost done with one part of the problem. One part of the problem was to figure out how quickly does the velocity change, does the potential energy change in the limit. We could plug that right in to mg. So for the second part, the derivative of the potential energy as in the limit as t goes to infinity is mg times the height as a function of time, which is mg times g tau. And that is mg squared tau. So you can plug in the numbers for the mass and g and the tau, and you'll get a particular value in joules per second for how much energy is being lost, because in the limit, the potential energy is the only thing that's changing. And therefore, all of that energy is getting converted into heat. But then there was another part of the first part of the problem asked for the explicit form of the function. At what rate is energy being dissipated before the parachute opens, not in the limit. Okay, so we want a function describing the rate at which energy is being dissipated. So not in the limit, we need to ask, as it's falling, some of that energy is being turned into kinetic, and some of it is being turned into potential. I'm sorry, and some of it is being turned into heat. So potential energy is dropping, kinetic energy is increasing, and thermal energy is increasing. We want to know how much. So that part, slightly more complicated. We need to know exactly how the potential energy is changing and exactly how the kinetic energy is changing. So basically, we need to know what's the derivative of the potential energy, what's the derivative of the kinetic energy, and if they're equal to each other, no heat is being generated, because every bit of potential energy that decreases is matched by an amount of kinetic energy that increases. But if they're not equal to each other, the difference must be how much heat was generated. So we want to figure out expressions for the rate of change of potential energy and rate of change of kinetic energy, and we want to subtract them, because that'll tell us how quickly the difference. So to do that, we need to know the derivative of the mgh function and the derivative of the 1/2 mv squared function. That means we need functions for the height and the gravity as a function of time, and we need a function for the velocity as a function of time. So I'm going to stop here for right now, because this is already getting long enough as a starting point. And I want you to give it a shot for part A of this problem using this idea. And this is the answer for part B. You just need to plug the numbers in. So to quickly review, the idea is as the package drops, potential energy is obviously decreasing. Kinetic energy is increasing for a while. And then after a while, the kinetic energy stops changing because the acceleration has shut off. At that point, all the potential energy is being turned into heat. And therefore, that's the rate at which heat is being generated in the long time limit. And before that, some of the potential energy is being turned into heat and some of it's being turned into kinetic. And we're trying to figure out what's the difference between them, because that'll tell us how much heat is generated. Okay.